Welcome and thank you for standing by. I would like to inform all parties that today's conference is being recorded. If you have any objections, you may disconnect at this time. Please note all participants are in listen-only mode until the question and answer session of today's conference. At that time, you may press star one on your phone to ask a question. I would now like to turn the conference over to Abby Interante. Abby, you may begin. Thank you.
Thank you. Good morning. My name is Abby Interante, and I work in communications at NASA headquarters. I'm excited to have all of you here today to learn about these great missions we have launching later this month, including tracers, which will help us to understand the impacts of space weather on Earth's magnetic field. Launching with tracers are a few rideshare missions: Athena Epic, Hex, and the real CubeSat. Joining us today are Joe Westlake, the Heliophysics Division Director at NASA headquarters, David Miles, Principal Investigator for Tracers out of the University of Iowa, Corey Priestley, Principal Investigator for Athena Epic at NASA Langley, Greg Heckler, Deputy Program Manager for Capability Development for SCAN at NASA headquarters, and Robin Millen, Real Principal Investigator out of Dartmouth College. Today, you will first hear from each of our experts, and those who have dialed in will have the opportunity to ask questions. So, to start us off, we will hear from Joe Westlake. Joe?
Hey, everybody. Good morning. My name is Joe Westlake. I am Director of Heliophysics here at NASA headquarters. First off, what is heliophysics? According to Merriam-Webster, heliophysics is the scientific study of how the sun works and how it affects the solar system. In case you missed it, the word heliophysics was recently added to the dictionary by Merriam-Webster. It's characterized as slang. We're kind of entering our slang era to some degree, right? But the fact that it's now in the dictionary and it's now on its way to becoming a full-fledged word is really exciting and a huge step forward for this discipline, for my colleagues, and for the study of the sun and its effects on the Earth. At NASA, we really focus on that study, and we do that for the benefit of humanity. This includes how the sun's influence on everything in the solar system, including space weather, and how it affects us here on Earth. Tracers is a key part of that. Tracers, it's a pair of satellites that'll study how the solar wind interacts with and enters our Earth's magnetosphere. This is the region around our Earth that is dominated by the planet's magnetic field, and it protects us from the stellar radiation and really from everything else that's going on in space. What we will learn from tracers is critical for the understanding and eventually the predicting of how energy from our sun impacts the Earth and our space and ground-based assets, whether it be GPS or communication signals, power grids, space assets, and our astronauts working up in space. It's going to help us keep our way of life safe here on Earth and help to continue to enable safe space exploration. Speaking of space weather, when we think about that, we think about things like solar flares, coronal mass ejections, solar particle events, and geomagnetic storms, all coming from the solar wind and its impact here on the Earth. They're all components of this space weather that comes to impact us here on Earth, but also throughout the solar system. Understanding our sun and the space weather it produces is more important to us here on Earth, I think, than most realize. Every human on Earth, as well as nearly every system that's involved in space exploration and human needs, is affected by space weather. Every day across the world, people deal with the effects of space weather, and you may not realize it, but let me give you a couple of good examples. Whether it be a farmer in Middle America who stops their planting operations due to a poor GPS signal for their precision planting operation, a power grid manager who changes the configuration of their network to ensure blackout doesn't occur due to voltage instability, or maybe a pilot who switches to backup communication equipment due to loss of high-frequency radio. A commercial internet company providing service to the military and others must change the orbit of their spacecraft to avoid collision due to increased atmospheric drag. Or maybe just, think of yourself as a child or a 9-year-old child sitting on their father's shoulders and gazing in awe at the beautiful aurora light show that has become increasingly more common for us to see. In 2024, May last year, we saw this giant Gannon storm. This G5 storm was the largest geomagnetic storm that we've seen in the last 20 years. And we saw these impacts across many industries. I hope that many of you, even down in Iowa and other places, I know we have a couple of folks from across the country here, were able to see the aurora light show that happened because of that great solar storm. But it also had additional impacts, whether it be in aviation, where transoceanic flights were rerouted due to high-frequency radio loss, and precision landing and performance-based navigation systems were unavailable for some time. There were indirect impacts to the travel industry, like delays and interruptions because of this. Roughly $500 million in economic loss from precision GPS issues in the agriculture sector, economic impacts and losses that are typically passed on to the consumer in this case. And then we had high voltage lines trip across northern Europe, and an interruption of service, as well as some of our satellite operations that we're becoming more and more reliant on, where we saw over 5,000 satellites see increased atmospheric drag, resulting in more frequent station keeping and autonomous collision avoidance maneuvers. And it also impacted the space industry, where we have our astronauts operating up in space on the International Space Station and others, as well as other industries that rely on this data. So Tracers joins the fleet of current heliophysics missions that are actively increasing our understanding of the sun and space weather and how to mitigate these impacts. Tracers is a collaborative effort between government, academia, and industry, and I'm really grateful for the participation of all of our partners, and you'll hear from a few of them in this telecom. I'm also very excited to be a part of this rideshare and have all of the missions that are coming along with us, showing that efficient use of government funds to get more science into space on the dollar, and really thrilled that Tracers is hitching a ride to space with these other great missions that you're going to hear about. At this point, I'm going to actually pass it on to the principal investigator of the Tracers mission, David Miles. Why don't you go ahead and take it away?
Thank you, Joe. So my name is David Miles. I'm an associate professor in physics and astronomy at the University of Iowa, and I'm also the principal investigator for Tracers. Tracers stands for the Tandem, Reconnection, and Cusp Electrodynamics Reconnaissance satellites. But really what Tracers is doing is it's going to study how the output of the sun couples to near-Earth space. So the sun is a burning, fiery ball of plasma, and as it burns, it blows off an exhaust that we call the solar wind. It's a plasma, and that's always streaming from the sun towards the Earth, and sometimes the magnetic field of the Earth basically stands it off, in the same way that if you have a rock in a stream, the water kind of flows around it. But other times, those two systems couple, the system of the solar wind that's blowing at the Earth and the system of the magnetically dominated region around the Earth. And when those systems couple, you dump mass, energy, and momentum into the Earth system. And that's the primary driver for, beautiful things, as Joe talked about, like the northern lights. But it also drives some of these negative things that we want to understand and mitigate, like unplanned electrical currents in our electrical grids, can potentially cause accelerated aging in electrical pipelines, disruption of GPS, things like that. So what we're looking at trying to understand is how the coupling between those systems changes in space and in time. So a long-term challenge to studying this is that because you study this from a satellite, you fly a satellite through the region where magnetic reconnection is happening, or a region that you can study it from, and you get one snapshot of what the system looks like. The satellite then goes all the way around the Earth. It comes back something like 90 minutes later. You get another snapshot, and it's different. But you can't tell, is that because the system itself is changing? Is that because this magnetic reconnection, the coupling process, is moving around? Is it turning on and off? And if it's turning on and off, how quickly can it do it? So those are fundamental things that we need to understand in order to understand how the solar wind arriving at the Earth does or doesn't transfer energy to the Earth system, which has this downstream effect of space weather. So we have two spacecraft. This is the novel part of Tracers, and they're going to follow each other at a very close separation. So one spacecraft goes through, 10 to 120 seconds later, the second spacecraft comes through. That gives us two closely spaced measurements that allow us to pick apart, is something accelerating and slowing down, is something moving around, is something turning on and turning off. Each spacecraft is going to get a measurement of basically the local state of the plasma. So that's things like the electric field, the magnetic field, and the local ions and electrons that compose the plasma. We have instruments built, both here at the University of Iowa and through our partners at UCLA, Berkeley, and Southwest Research. The two spacecraft are provided by Millennium Space Systems, which is now a Boeing company. And so we have these two well-instrumented spacecraft that make two closely spaced snapshots that allow us to understand how things change. What we're looking at right now is getting the spacecraft, basically ready to launch. We're on site at Vandenberg Space Force Base. We're really excited to get on orbit and to do some great science. At that, I will pass it off to Corey.
Thank you, Dave. So my name is Corey Priestley, and I am a senior research scientist at NASA's Langley Research Center, and I've had the privilege to serve as the principal investigator for the Athena Epic multi-agency mission. The name Athena was chosen for this mission because Athena is the goddess of wisdom and strategy, which are two characteristics that this mission encompasses over its life cycle of intelligent collaboration with an all-of-government approach with agencies who have similar needs to place assets on orbit in a rapid, cost-efficient, and reliable manner. So coupling into the science, the Earth is a heat engine which obtains life-sustaining energy from the sun in the form of sunlight. And so in keeping with the theme of tracers being a heliophysics mission, while Athena does not observe solar physics directly, as does tracers, it does observe the impact of the solar thermal energy portion of the electromagnetic spectrum arriving at Earth has on the Earth atmosphere system. The sunlight absorbed by the Earth atmosphere system warms our planet. It drives the energy flows in the oceans and atmosphere, such as weather systems, ocean currents, and the seasons. And in order to maintain a balance with its surroundings in the universe, the Earth emits roughly the same amount of energy as it absorbs from the sun as thermal or long-wave energy. Athena will observe this outgoing long-wave radiation emitted by the Earth, mapping this critical element and helping society to understand the dynamic energy flows of the Earth atmosphere system. So this information is critical to multiple sectors of society, such as long-term weather planning, agriculture, renewable energy, and land use planning, among many others. So NASA has been making these global measurements from space utilizing the current clouds in the Earth's radiant energy system, or SERIES instruments, since 1997. Athena is not about a new approach to making these observations, but rather reimagining the way we fly these critical instruments moving into the future. So Athena is a programmatic and technical pathfinder which reimagines the legacy series missions, capitalizing on a new innovative satellite architecture and completing a space vehicle which right-sizes a satellite to only what it needs, providing a complete observatory in space roughly equivalent in size to the original series instrument, which is roughly the size of the small electric car that my granddaughter drives around my house. So previously, the series instruments have flown on large satellites roughly the size of a school bus. This reimagining has been made possible by the development of hyper-integrated satellites, or HISATs, by our commercial partner, NovaWorks. The HISATs are unique building blocks, each about the size of a toaster you may find in your kitchen, that connect, similar to Legos, with each other and can form around the science payload elements and integrate with them, sharing resources and providing control functions, ultimately resulting in a new type of space vehicle, which we call a sensor craft. So Athena Epic represents the first flight of a long-term effort at NASA Langley to continue the observations initiated by Ceres in the late 90s and provide persistent observations and monitoring of the Earth's energy budget over the next several decades. So I'd like to recognize the government partners for Athena include NASA, NOAA, and the U.S. Space Force, with NovaWorks, who developed the innovative hyper-integrated satellites building block as our commercial partner. So now I'll pass it along to Greg Heckler from the Space Communications and Navigation Program.
Hey, good morning, everyone. I'm Greg Heckler, and I do indeed work in NASA's Space Communication and Navigation Program, which we refer to as SCAN. Our job in the agency is to manage all the space communication activities, projects, programs, and infrastructure to enable science and exploration missions. We help lead the charge in connecting all of the human beings on Earth to those missions out in the solar system, whether it's beaming those new images from James Webb, communicating with the Voyager spacecraft now outside of the solar system and interstellar space, or returning live video from those astronauts that will soon land on the moon. We make that happen. From launch to landing to everything in between, we actually keep over 100 missions connected and on course every day. You can think of us, our motto, we're the universe's best internet service provider. So today I'm here to talk about the Polylingual Experimental Terminal, or which we call PEX. That mission's goal is to bring seamless, uninterrupted connectivity to our next generation of space missions. I'd like to draw an analogy to what we know and love, cell phones. 20 years ago, your cell phone experience was not that great. You could call it kind of crappy. If you went on travel on a car trip outside of your city, your town, your state, you might not be able to connect at all. Or if you did, you might get hit by huge roaming fees. But today, you can hop on a 15-hour international flight to Tokyo, to Seoul, to South Africa, to Paris, and you walk outside of that airplane door with your iPhone or your Android device, and it just works. We want future spacecraft to benefit from these same capabilities. So to pave that way, the PEX mission will demonstrate this in low Earth orbit by communicating across NASA's legacy tracking and data relay satellite fleet, which we call TDRS, and 2 commercial networks, something that actually has never been done before. The PEX payload has 2 key technologies to allow this to happen. One, just like your car radio, this terminal, this communications terminal, can tune across a wide range of the radio spectrum, allowing it to access these different space communication networks. And second, the terminal can speak the different languages each of these networks uses, what we call protocols. And so just like the universal translator on Star Trek or the Battlefish from Hitchhiker's Guide, we put that magic in this payload. We love doing partnerships in our program, bringing together different communities where we all co-invest to achieve mission objectives, where we all benefit is an amazing thing. And so we partnered with 5 members of industry and academia to achieve this mission. Johns Hopkins Applied Physics Lab developed the terminal and is managing the project for SCAN. The terminal is mounted on a York Space Systems bus, and they actually procured the launch itself and will be operating the spacecraft for the first year, the demonstration. And during the demo, PEX will communicate across our TDRS constellation and 2 commercial networks, SES's O3b mPOWER network, which is being actually established as we speak, and Viasat and Boeing's Global Express network as well. And we're really proud of our ability to lead this agency into a new era of space communications as we work to commercialize our near-Earth portfolio. Our missions are already starting to consider the strategy, and we'll be taking this commercial first approach in the 2020s. And for those early adopters, this technology demonstration through PEX could be a game changer, revolutionizing how they connect, communicate, and collaborate with private industry and networks. We take our job very seriously in bringing these new capabilities to enable new science and exploration. That's the best job in the agency, so we're very proud of it. So thanks. I hope there's some good questions, and I'm going to turn it over to Robin, the principal investigator for REAL.
Hi, everybody. I'm Robin Millen. I'm a professor of physics and astronomy at Dartmouth and PI of REAL, which is the relativistic electron atmospheric loss CubeSat, which will study Earth's Van Allen radiation belts. The radiation belts are a region of Earth surrounding the Earth that are filled with high energy charged particles that are traveling at near the speed of light. These are sometimes called killer electrons because these particles are a hazard for our satellites in space. They also rain down on our atmosphere where they can contribute to ozone destruction. So REAL will help us understand how these particles get scattered out of the radiation belt and into the atmosphere. Despite its small size, so REAL is a CubeSat, it's only about 1 foot long and less than 10 pounds. It carries a powerful particle sensor that will, for the first time, make very rapid measurements of these electrons as they enter our atmosphere. And this is really critical for understanding what's scattering them. The sensor was built by APL based on their experience with particle sensors. But what's unique here is its small size. So it's small enough to fit into a CubeSat. And this is another important goal of REAL, is getting spaceflight data on this new miniaturized instrument design. This technology advancement could enable future missions, especially those requiring constellations of satellites. REAL was funded by NASA's Heliophysics Flight Opportunities in Research and Technology program, and it's living up to those dual goals of that program to advance science and technology at low cost. The REAL spacecraft was primarily built by students and early career engineers at Montana State University, so it's also serving an important workforce training goal. We're really excited to get the data finally, and I'm especially excited to be launching with tracers. We've already started thinking about some of the science synergies that we could get with combining our data, but also because University of Iowa is, of course, famous as the place where James Van Allen spent much of his career. Van Allen discovered the radiation belts with the first U.S. satellite, Explorer-1, so it's very fitting for REAL, another radiation belt mission, to be launching with a University of Iowa mission. Thanks.
Thank you, everyone. We have now reached the question and answer portion of our call. You may press star 1 to enter the queue. I will pass things over to Chanel to help with unmuting callers.
Thank you. As Abby said, we will now begin the question and answer session. If you would like to ask a question, please press star 1, unmute your phone, and record your name clearly. Your name is required to introduce the question. If you need to withdraw your question, press star 2. Again, to ask a question, press star 1. It will take a few moments for the questions to come through, so please stand by. At this time, Abby, I see no questions in queue.
Okay, we are seeing a few on our end, so just give us one moment to move folks into the right section.
Chanel, I see a question from Will Robinson Smith. Are you able to unmute him?
Certainly. One moment, please. Will, your line is open. Will, your line is open.
Yes, can you hear me?
Yes.
Perfect. Yeah, Will Robinson Smith with Spaceflight Now. Thanks for taking the time to talk with us today. Maybe quickly, just down the road to all the PIs, for the total cost of each of your programs and payloads, and then specifically to the folks with Athena Epic, can you expand more about the Space Forces and NOAA's role in this mission? Thanks.
So would you like Athena to go first?
Go for it.
Okay, so this is Corey Priestley. The total life cycle cost of Athena from cradle to grave, I call it, end of mission, is about $15 million, so it's a relatively inexpensive mission overall. And the relative roles between Space Force, NOAA, and NASA, all agencies are looking for more rapid and reliable access to space. And so that was the genesis of it. And Space Force has provided the contract mechanism with NovaWorks. They had the original contract. NOAA is keenly interested in more commercial applications as they venture forward from JPSS into the NEON program for the National Weather Service moving forward. And NASA, again, is looking for rapid, low-cost access to space for multiple observations.
Yeah, hey, Will, and I can cover it for Tracers and REAL and others. So Tracers is a part of our Small Explorers mission. That is a mission that it has a cost of $170 million. And REAL is one of our CubeSat missions that has a cost of $5 million. I'll note that this launch opportunity as well is a great and efficient way for us to get to space, and it's really saving the taxpayer dollars by linking multiple missions on a singular launch. Great question.
Okay, thanks, Joe. And then, Greg, do you have a cost available for PEX?
Yeah, certainly. The life cycle cost for that mission is about $20 million. Thank you.
Okay, great, thank you. Next, I see Jeff Faust in the queue. Chanel, if you could unmute him. Thank you.
Jeff, your line is open.
Good morning. This is Jeff Faust of Space News. Question for whoever wants to take it. Do you have a target launch date for the mission? And are all the payloads going to the same orbit, or will some be deployed in different orbits? Thank you.
Yeah, thanks, Jeff. So the launch date is no earlier than late July. And as far as the orbits go, so, we're going into a low Earth orbit with tracers, and maybe others could speak to the orbits that they're aiming for the different missions.
Yeah, Jeff, Greg Heckler. PEX will be going into low Earth Sun-sync orbit, along with the rest of many of the other ride shares.
So from the tracer's perspective, we're going into a 590-kilometer sun-sync orbit, and I believe that SpaceX is actually basically making 2 stops to drop some of the spacecraft off at one altitude and then some of the spacecraft off at another.
Yeah, I'll just add to that. And Real is going to be at 510 kilometers, so below Tracer. So that's one of the things we're kind of interested in is with the data that Tracers is already collecting, we'll have some cases where we're right below them making measurements, which will be really interesting.
Yeah, and Athena will be going into about a 500-kilometer sun-sync orbit as well, 10:30 crossing time.
Okay, thank you. Next, I see Madeline Durrett in the queue. Chanel, if you could unmute her. Thank you.
Hi, yes, it's Madeline Durrett with Payload Space. This is for whoever would like to answer it. Do you see the findings from tracers leading in the long term to new satellite insurance models, compliance standards, or operational protocols for businesses that might be vulnerable to space weather?
So that's a great question. Thanks, Madeline. For the most part, our first goal with these missions is to attain the science that they were aiming for, right? So a lot of the data that we produce and the information that we produce off of tracers is to solve some of the fundamental scientific understanding of how energy comes into the Earth system. Having said that, we frequently find cases where that data becomes useful, whether it be to operational entities or it becomes useful to all sorts of different places. When we find that data is useful or we've spoken to that user or that application, a lot of times in our space weather program, we can find ways to create applications that help that. For tracers specifically, we don't have any space weather data that is directly coming down on a sort of operational link side of things. But as we see the value and as we get through the science of this mission and really deliver on the fundamental understanding of our magnetosphere, I think that we'll find it to be the case that this tracers data is very useful for informing space weather in the future. So we look to that future and hope for it.
Thank you.
Yeah, and if I could just add, so tracers is, fully compliant with, the spirit and the letter of the NASA open data policies. So all of the data that we make, we get it on the ground, we process it, we get it calibrated, and then at very low latency, we will be making it available, on the website to really anyone who wants to use it. So once we're on orbit and we're operating, this data becomes available for, our team, for the broader scientific community, and really for anyone else that can make, good and productive use of it.
Thank you. And just as a reminder, you can press *1 to enter our queue. We actually have a question from Facebook. So Ahmad on Facebook asks, does the sun have magnetism? So David, could you maybe talk about how the sun's magnetic field interacts with Earth?
Absolutely. So the sun is a big, basically burning ball of plasma. And that plasma is confined by this, monstrous and complex magnetic field of the sun. And there's this cool physics phenomena called the locked-in condition, which is in a magnetized plasma, if you move the particles of the plasma, the protons and the electrons, it drags the magnetic field with it. And if you drag the magnetic field, it brings the plasma along with it. So the stuff that is being created as the exhaust of the sun, the solar wind, is this plasma of, basically very ionized gas that is being pushed and dragged and is pushing and dragging the magnetic field of the sun. So when that magnetized plasma arrives at the Earth, it arrives at this sort of dominated magnetic region around the Earth created by the Earth's magnetic field. And the thing that is interacting is the magnetized plasma of the Earth interacting with the magnetized plasma of the solar wind. So it's all coupled together, and this whole system is basically threaded by the relevant magnetic fields. It's a great question.
Great. Thank you so much, David. I see Will Robinson Smith in the queue. If he could be unmuted, please.
Well, your line is open.
Great. Thanks for allowing for another question. Maybe going back down the row of the panelists again, can you just briefly touch on the expected operating life for each mission? And then specifically to Greg Heckler, can you expand upon how the commercial partners, SCS and Boeing, were chosen to partner up with this experiment? Did they come to you guys, or did you reach out and just put out some feelers to the various communications operators working in LEO and beyond? Thanks.
Okay, thank you. We can start with Joe to answer your question.
Yeah, so within our Explorers program, generally supports missions that have a relatively short science main timeline. So their prime mission is how we usually refer to that. And it's interesting because most of our Explorers tend to live well past a singular solar cycle, so well past 11 years. We have actually a great track record of our Explorers living significantly longer than their design lifetime. Tracers has a 1-year Phase E, a 1-year prime mission timeline, but we expect it to obviously stay operational and other things for some time afterwards. And then our CubeSats are usually run at a higher risk profile, and they're usually run in a way in which the design lifetime is roughly a 4-month lifetime. And they usually stay up for quite some time after that. And then Greg, I can probably pass it off to you.
Yeah, certainly. Yeah. So for PAX, the York satellite system bus is anticipated to last 5 years. That's its design lifetime. Right now, we only have about 6 to 9 months, kind of call it programs, for the demonstration. The great thing about the payload we're building is it actually can communicate with other networks. So once PEX is up there and operating, we'll probably do that work of considering, is there a more valid value-added demonstration, and consider a lifetime extension beyond that initial 6 to 9 months. To answer your question of how we ended up with SES mPOWER and Global Express, APL is the principal of the project lead for this demonstration. And so we set a goal with them of talking with TDRS, communicating with TDRS, and at least 2 other commercial networks. They went out and engaged with the commercial SATCOM community, looked at cost of services, technical feasibility, kind of the performance, the value we could see in the demonstration, plus timing. mPOWER is being built out as we speak, and so we were trying to match the PEX launch with potential emerging capabilities as well. And so working with APL, we chose these 2 service providers initially, but as I mentioned, are exploring other opportunities in mission extension. We're very interested not only in talking to satellite relay constellations, but potentially ground assets, ground antennas networks, like KSAT, SSC, Amazon Web Services, or others in the future.
Thank you. And Corey, could you touch on the life cycle of Athena Epic?
Sure. Athena Epic currently has 12 months of funding for operations from the DoD Space Test Program. However, the design lifetime of the hardware is significantly longer than that. So if we do prove successful, we anticipate being able to fly much longer than that to continue the demonstration.
Great, thank you. I don't see any questions in our queue, so I just want to invite you to please press *1, and I'll give it a few moments to see if anybody else joins in.
Just while we're waiting for that, adding on the tracer's perspective, So we designed the mission, we designed the spacecraft so that we're confident that we can do all of our baseline science in that 12-month period. But the tracer spacecraft are basically two flying plasma laboratories, and we have significant margin in terms of things like propellant and design life. So once we're through our baseline science, that platform becomes available for other scientific uses if that's appropriate.
And I'll just add for real, as Joe said, we're aiming for a 6-month mission for science mission, but we do expect the spacecraft, the real spacecraft, to deorbit naturally after about a year.
Great, thank you so much. I haven't seen anybody else join the queue, so we can wrap things up here. You can find more information and updates about tracers at nasa.gov/tracers. On that page, there is a press kit and also a link to NASA's Scientific Visualization Studio, where there are pre-recorded video interviews, B-roll, animations, and spacecraft imagery that you are welcome to use. And actually, I just saw somebody join our queue, so we will open it up for just one more question. Could you please unmute Ella?
Hi, I have just
your line is open. Thanks.
Oh, perfect. Okay. Hi, I just have one question. After the equipment has its life cycle is over and it is its timeline is done, what happens?
Ella, were you asking about a specific mission?
For all of them.
For all of them. Okay. Then we can go ahead and go down the line.
Yeah, I'll just give a generality. In general, these missions are, because they're in low Earth orbit, and there are many other spacecraft in low Earth orbit, NASA, as a responsible user of space, is usually looking to deorbit many of these spacecraft when we get to the end of lifetime. You heard Robin mention the sort of deorbit timeline on the CubeSats, and usually, we have a sort of risk-reward calculation where we're trying to figure out the length of time that we can maintain a space asset safely up in orbit. So these things usually at some point we will deorbit them, which means bringing them out of space once they've gotten past their usable lifetime. And the spacecraft, the missions themselves can probably speak specifics to them, but I think that covers it in the general sense.
Yeah, so from the tracer's perspective, we are by design in an orbit where, we could just naturally let that orbit decay and we would meet the requirements for, deorbiting in a limited and appropriate amount of time. We also have, significant propellant capability, so we could choose to expedite that and deorbit more rapidly. Typically, at the end of mission, we would do what's called passivating the spacecraft. So basically, if we had fuel left, we would vent it. We would drain all of the power out of our battery. We would basically scrub the computer so that it's blank and can't be used. And that basically makes the spacecraft safe so that if something were to happen, so there's very little energy left in the spacecraft, and then we would either naturally let it decay in its orbit, or we would make an intentional burn to deorbit the spacecraft.
For Athena, we are not carrying propellant to deorbit. It will be a natural decay, and after we complete our prime mission, we will again passivate the spacecraft and place it in an orientation with maximum drag to accelerate the decay.
Yeah, for PAX, it's the same situation as Athena. There's no onboard propellant, so we'll passivate and increase drag to naturally decay as quickly as possible.
Okay, thank you so much, everybody, for joining. I don't see anyone else in the queue, so we can wrap it up now. Please reach out if you're interested in arranging an interview or have any additional questions. And thank you so much for joining. Have a great day.
This concludes today's conference. All participants may disconnect at this time. Thank you. Speakers, please stand by.